Hi everybody, this is Farhan from AlgosFromScratch, and I welcome all of you to this amazing playlist, building a DistilBERT model from scratch using PyTorch. So this is going to be the third video of this playlist. In this specific video, we are going to start the first coding practice of the playlist. Okay, so previously we discussed some theoretical parts where we discussed the roadmap. We discussed the architecture of the model. We discussed the backbone, that is the transformer architecture. So this specific video now is going to be on the next step in our roadmap that I have already shown here. Download the DistilBERT model and use it for sentiment analysis. Okay, so we are going to follow some steps in this. Let me just quickly go through the steps that we are going to follow in this specific video. So first of all, we will load some data set from Hugging Face. Load data set from Hugging Face. Then we will explore the data set, of course, and then we are going to load, or if it's not downloaded, so to download the model, and it will be the DistilBERT model, and also the respective tokenizer it is going to use. Okay, so every model has its own tokenizer, and that tokenizer basically decides what integer values the model is going to assign to the subtokens in the text. Okay, and then we will prepare the training arguments. So training args, we will prepare training arguments, and we will prepare our trainer object, where we will pass all of our configurations, and then we will train the model. And during the training, by the way, we are going to evaluate the model with the help of matrices. In this case, we will be using accuracy and F1 score. Okay, so finally we will test the model, test our model, this fine-tuned model. Okay, on the basis of this this data set that is basically the sentiment analysis to its data with 3 classes. Okay, so we will then test our model. So by the end of this video, you will be able to fine-tune any model on your domain data. Okay, so if you are working in some specific domain, you can perform these steps, and then the model that already is pre-trained, but when we load the model with randomly initialized classification head, basically we need to train those weights. Okay, otherwise those weights are going to give us random logits. So first we are going to pass our data, like the domain data, and train the weights first. Okay, once the model is trained, we then load the model and then we use it for our tasks. Okay, so these all steps we are going to follow, and I am going to open the Google Notebook. I've written this code so we can save some time. Of course, our goal is not to learn Hugging Face library and how to work with Hugging Face library. We are just going to see how Hugging Face basically performs all these. Let's just execute this code live right here. Okay, this is just the command. You can see -q, it kind of suppressing the installation outputs on the screen. And then we have this data set. We will be using it to load the data set transformers. We'll be using this to import these auto tokenizer or the auto model classification sequence for sequence classification, like libraries classes, and we will be using these libraries to download our model and tokenizer so we can use it. Okay, then we will be evaluating the model. So this evaluate will basically gives us the matrices for evaluating our model. Okay, then sklearn for some machine learning tasks. This Hugging Face hub, it's not, we are not going to use it. It's basically we can like push our model to the Hugging Face hub. Here is we are importing the torch library, this library for tensors calculation. Okay, and then this auto tokenizer. Okay, this auto tokenizer basically is it's a class in the Hugging Face. We can use it to we just pass the you can say checkpoint name, like the type of task, and it gives us the tokenizer against that specific task by auto modeling it in internally. Okay, so again, as I said, this Hugging Face library is the wrapper. You are not going to perform most of the tasks. You are just going to call these libraries, these classes, and these classes internally will be doing all this stuff for you. Okay, so here torch.cuda is available. It's simply I'm just checking the GPU if it is, yeah, it is connected. So here, okay, this is the data set. How we load the data set, we basically use this load data set from the data set class that we downloaded here. We are going to execute this, and we will see the data we will be downloading the data on our system. Okay, here, so we can access the data then. Okay, this is the tweet evaluation data sentiment analysis task. Okay, so let's let's see what we have in the data set. Okay, here you can see the data set contains train, test, and validation split. Okay, so we perform this splitting. If you have been doing the machine learning, where we used to import the train test split from the sklearn library, but here we have already this data ready in 3 different splits. One is train, the second one is test, and then this validation. So these 3 kind of splits we use specifically while training our model or fine-tuning our model. Okay, so training data we will be using for training. Validation we use to test the basically the overfitting of model. Okay, so we during the training we pass some validation data, and this validation data is the unseen data. Okay, so model needs to be a bit generalized. It needs to learn the features, not memorize it. So that's why we pass the validation data, that is the unseen data, to the model during training. Okay, we can use the test data later on for predictions and evaluation. Okay, and then this is where I am basically printing to show you the data set train, data set test, and validation. Okay, so here you can see this is the text of each tweet and the label against that tweet. We for now we don't have any idea what this 2 means basically, and what this 1 means. Okay, but we will find this out. Okay, this collection counter, basically I'm importing. This is used to count the number of keys and its values. Okay, here we can pass test. So if we count it, you can see the number of labels against each class. So against 1 we have these number of rows against the second class, and this third class, that is 0. Let's say if you have 2 classes A and B, you have 10,000 rows for class A, and you have just 500 rows for class B. So that is going to be the imbalanced data set. So we just quickly check that. Okay, so here you can see we have almost equal number of class distribution here. So that is not that much imbalance in the data. So we are good to go. We are going to get the features labels, and what we are going to do with this now, it will basically extract the feature labels and basically the label names against each class. Okay, so here we have till now extracted that there are 3 labels against 3 label integer values, okay, like 0, 1, and 2. Okay, so now we have a bit idea that we have these 3 labels, but to make sure that these labels are mapped to which integer values, so we can then get the label features of the same you can say all these label features we are getting. Okay, and okay, then we are basically on this label feature are calling this function integer to string. Okay, and we are passing one by one the integer values to this. Okay, so if I show you, you can see we have negative, we have neutral, we have positive. Okay, so it means 0 is mapped to negative, neutral is mapped to 1, and positive is mapped to 2. Moving on, this is the model checkpoint. So here I am just writing DistilBERT base uncased. So there are 2 kind of models. One is uncased and cased. Okay, so uncased means it basically converts all the capital letters to the lower case values letters, and then it processes it for the purpose of efficiency. Now we pass it to the auto tokenizer. Okay, this auto tokenizer from pretrain, when we pass this model checkpoint to this, so what happens, it gives us internally, it maps it to the specific tokenizer, and then it starts downloading it. Okay, so as I mentioned again, this is the issue with these libraries, that we do not know what's going on under the hood. Okay, and that is what we are going to explore in this playlist. Okay, that is my purpose. I don't want you guys to be very dependent on these frameworks. These frameworks are for experimentation purpose. Okay, so you can quickly experiment with models, or for so we are going to explore how these libraries work internally. Okay, so if I execute this code, what will happen, we will get the model tokenizer. Okay, so here you can see this is config.json, all the configurations for the JSON for the tokenizer, tokenizer config.json, vocabulary text, and JSON tokenizer.json. Okay, so at this stage now we have downloaded the tokenizer. Okay, and this tokenizer downloads all these configuration files and vocabulary values. We are going to explore them. So this tokenizer object will later on use these configuration files to convert our text into input values. Okay, so moving on, let's check what vocabulary set we have in the tokenizer. Okay, so there is a function, there is a method in the tokenizer that is get vocab. Okay, I am going to call it this. Okay, so if I show you this right here, let me copy paste it and run it. So if I now show you this vocab, okay, and let's see what we have. So okay, this is the key value pairs, and if I quickly check its type, okay, let's see. So it's a dictionary. Okay, so we can call this dot items on it to extract the key value pairs, and we are going to store it in vocab. So it is going to give us the key value pairs, total key value pairs. Okay, so vocabulary is basically how much vocabulary size this tokenizer contains. Okay, so this contains each token at the time of tokenizer building, and all these tokens are then stored with their integer values. So each time we pass the text to this tokenizer, this tokenizer is going to extract the integer value against each token or subtoken, and then the integer value is going to be the input IDs for the embedding layers. Okay, so if I show you the length, we have 30522. That is the vocabulary size of this tokenizer. Okay, we have nowadays we have tokenizers, they have values of more than 100k, like around 128 or 150k. So they cover more area, more vocabularies. Now what I am going to do here, basically this is the last 10 elements that I am getting from this vocabulary items. I'm basically converting it to a list, and then I am slicing on it with negative indexing. Okay, so here you can see these are the tokens and their respective values. Okay, like this. So yeah, now here is the specialized token, or you can say special token mapping of this tokenizer. You see, every tokenizer nowadays, they have this special tokens mapping. What does it mean? These are used for some specific purpose, or you can say the just say like here, this unknown token. Okay, so this unknown token basically means is if we have some out of vocabulary, we have OOV concept. Okay, when we encounter the OOV, like out of vocabulary, some word comes in the text that is not in the vocabulary, so we so the tokenizer can assign unknown token to it. Okay, and these tokens have specific token IDs in the tokenizer. Then we have this separate. Okay, so we are not going to use this SEP for this specific, because this is used by the BERT and the models for the model pre-training. Okay, then we have paired tokens. This is very important. We are going to work with these paired tokens in our future videos. So this is very important. Then we have this class token. Of course, this is the one. This is the token that I was talking about here when I mentioned that this CLS token, basically, we use this CLS token to classify our class. Okay, so we are going to pass just this class token to the classifier head. Okay, then this mask token, we are not going to use this mask token because, as I said, it is from the pre-training configuration. So this mask is basically used for masked language modeling, MLM, and that is basically used for pre-training the DistilBERT model. So we are basically having this pre-trained model we are getting, and the pre-trained weights, and then we will be attaching the randomly initialized head as per our requirement. That is the 3 classes sentiment analysis task we are going to perform. So that is the whole idea. So that is why we have all these configurations, but we are not going to use it. Okay, then okay, we can separately check these token. Okay, so here you can see the CLS token is 101, the separator token is 102. So every time we pass the input values to this tokenizer, by default, this tokenizer will wrap the input between these 2 special tokens. One is 101, that is class CLS token. One is SEP token, that is 102. And then this padding is basically, I am checking this padding specifically whether I've been working on the other tasks. So there I wanted to check the padding token ID. So you can see here this is 0. So all these tokens, these special tokens, they have some specific IDs assigned to them inside the tokenizer. Okay, so here let's just test our tokenizer. Okay, here I'm going to pass this. I love this. This is the text that we are going to pass. Okay, and we are going to call this tokenizer. Basically has this encode function. We can call this function and we can pass the text to it, and it will basically encode the data. What we are going to get as a result, we are going to get the input IDs. Okay, so this tokenizer, with the help of encoder, now what it does, it first of all split your data into different tokens, and then it extracts the input IDs against each token, each subtoken. Okay, so let me show you here. If I just copy the same text, the same code here, and instead of here tokenizer, if in code, if I call this tokenize and show you token IDs, what token IDs has right now, it has I love this and this exclamation mark. Okay, so this tokenize plus input IDs extraction, both the steps we can perform with the help of this encode function. Okay, so quickly I am going to delete this. So this now has like all these values. So you can see we had 4 tokens. One, I love this and exclamation mark. Then by default the tokenizer adds these two values, 101, you can see up here, 101 for class CLS token, 102 for SEP token. So by default the tokenizer wraps these this input between these two special tokens. Okay, this I've been testing. Okay, so there is one technique that is used in the these tokenizers, these advanced tokenizers. I think this tokenizer uses the word piece tokenizer. So if I pass some lengthy kind of text or word to this tokenizer, what happens? This is the sub tokenization basically happens behind the scene. So maybe you one word can have a separate complete token as a single word, but sometimes it happens that it splits a word into 2 or 3 sub tokens. Okay, so I was testing it and I found that this is what happens with the subword tokenization. Okay, so this is the special identifier that is added to the sub token, which you can say is the part of previous token. Okay, so this is the identifier that this token is the sub token of the previous ones. Okay, and then okay, here is the another word. If I here, let's say tokenize it, you can see we have a lot of sub words against this word. Okay, so now you can see we have 1, 2, 3, 4, 5. Okay, and we have 5 words, subwords, and if I call this encode, we have 1, 2, 3, 4, 5, 6, 7. So 5 and 2 more. Moving on to the next code. Here is when we want to download the model itself. Okay, so just look into this. These two dictionaries, we are going to pass them to the auto model sequence classification class dot from pre-trained function. So these are the requirements. If you look into the documentation of the auto model for sequence classification dot from pre-trained, there we have these two parameters ID to label and label to ID. So basically, internally, this auto model for sequence classification is downloading the DistilBERT model. We are getting the DistilBERT model. I'm going to explain it right here. So what happens, this auto model will download the encoder part of the DistilBERT model. Plus, it already has the MLM head. So this is the master language modeling head, but we do not want this. So what we do when we call this auto model for sequence classification, it discards this head, and whatever we pass to it, like here you can see number of labels 3, it adds another head that is the classification head. Okay, so that is now the classification head. Okay, and this classification head basically contains a pre-classifier, then some dropout, and then the classifier, and finally the output is logits. Okay, so this part basically is randomly initialized. Okay, so we have totally randomly initialized values to these weights of the classification head. We have pre-trained weights for this encoder part. We fine-tune our complete model with encoder plus classification head. We will be performing the full fine-tuning. We are not going to freeze any weights here. We are going to just train the whole model. Okay, when we test or when we try to predict some text, so it can then, on the basis of a logit's position with the maximum value or the probabilities with the maximum value, it can then extract that specific winner, and against that winner it can give us this human readable classes. Okay, so it is just for that fine level of mapping. We also call this pre-trained from pre-trained method, and we pass the model checkpoint. If you remember previously, I named it DistilBERT uncased, and we pass the number of labels. We want to have a classification head that gives us by the end 3 values as a logit. Okay, so we will get 3 values as a logits, and then this is the mapping that we are passing to this, so we can finally then get the human readable labels, okay, at the time of prediction. Quickly going to the model configuration. Oh, okay, so first we download the model. When we execute this code, what happens, you can see here we are first of all downloading some safe tensors. This is the extension of storing the pre-trained weights. Okay, it downloads a configuration file, then it downloads the weights, and then on the basis of that configuration file it builds the complete architecture again. Okay, so while building the complete architecture, it gives us some warnings. Here you can see that we have some unexpected and then some missing. Okay, so unexpected here means we are the configuration file basically contains this master language modeling head. Okay, but here we do not have any layers for those values or for those weights. Okay, so that is where it says that this is unexpected, and basically it is throwing this part away. Okay, and then we have this missing. It means we are adding this pre-classifier pre-classifier weights, pre-classifier bias, and then this classifier weights and classifier bias. These are missing. It means these values are not in the configuration file of the model. Okay, so it means these are randomly initialized. So here you can see again this report here. It says those parameters were newly initialized because missing from the checkpoint. Okay, so consider training on your downstream task. Okay, so we are going to perform some downstream task. We will be training it, just like I mentioned over here, that we are going to train all this these weights in the classification head. Okay, let's just quickly explore the model configuration. Okay, here we have some activation functions like Gaussian. This GALU is basically being used as an activation function, and this is the architecture of the DistilBERT for masked LLM configuration. Okay, here you can see some attention dropouts, some beginning of sentence token IDs, dimensions. You can see 768, and then this dropout. So for now we are not going to focus on these, but of course when we are going to build our own custom model, there we will be looking into these values, and I will explain these values, how we can assign these values and where we assign these values. Okay, so this is the dimension. Basically it is the channel value of each token, and this is the token, this is the dropout percentage. We do not want some specific dimension memorize the data, so we randomly make 10% of the values to 0. Then this the precision type of the model, that is float 32, and also the sentence tokens. So some tokens we are not going to use, end of sentence token ID, we are not going to use them. Okay, and then hidden dimension, this is the dimension we use internally in the feed-forward neural network of the transformer block. Okay, so we have transformer block, as I mentioned over here. In this transformer block we have this feed-forward. Okay, and in this feed-forward, if I show you, here is this 3072 dimension. That is the dimension basically it is showing right here. Okay, then this is the ID to label and label to ID mapping. Okay, initializer range, the distribution range, some it is using for initializing the random values to the classification head. Maximum position embedding, very important. The maximum number of position embedding or position encoding that is available in this specific model. So if I show you, these are the positional encoding. So we have only 512 positional encoding. You can tune this data. Okay, so if you have some data that can have maximum of 100 tokens, so you can set it to 128. Okay, so whatever you want to do, you can do that with this value. Okay, it will then only have 1 to 8 positional encodings rather than 5, 1, 2. Then this model type, n head, n layers. Okay, number of head, and you can see 12, 6. Okay, so let me just show you this right here, so you can have a clear understanding. Okay, so if you look into this, we have this 12 heads over here at this transformer block. We have 12 heads. Okay, and as I mentioned that we have 6 blocks, so we have 12 heads and 6 blocks. It means this is the 6. Okay, so each input gets into first block, then output gets again into another block, and this basically is repeated 6 times. Okay, so this is what basically we are getting here in n layers. Pad token ID, QA, this is the question answer, we don't need them. Sequence classification, dropouts, we are going to use it in the transformer block. Okay, so this is the sinusoidal position embedding. We are basically setting it false because we want to make these positional encoding or these weights, we want them trainable. Okay, so we do not want some fixed sinusoidal positional embeddings. Okay, if you look into this attention is all you need paper where this transformer model was introduced, here you can see the formula of attention mechanism. We are going to implement all these steps one by one with the help of PyTorch. Okay, so here you can see the multi-head attention. All of these we are going to apply one by one in our upcoming videos. Okay, we have 5 feet forward. So here if you look into this, we have positional encoding, and this positional encoding, here you can see we have this formula. Okay, this is positional encoding. We use this sine and cos for alternative positions. So originally this idea of positional encoding was introduced by this paper, but there have been some changes to these concepts. So now we use the learnable parameters instead of the sinusoidal position embedding. Okay, this was the overview of this architecture. Once you understand this architecture, you can then build this with your own custom classes. Okay, we will be doing this in our upcoming lectures. Okay, so let's just quickly execute this code. This is a very easy code with model.parameters. Each time you get it gives you a generator. You just get each time trainable tensor, and that trainable tensor is we have this number of elements, basically numel, this method on tensors. If you call this, it gives you all of the elements in a tensor. Okay, so I am basically checking if all of the parameters are trainable. So if you have ever worked in the PyTorch, so you must be familiar with this required grades. It basically makes the parameter trainable. Okay, so the backward propagation basically, and the optimizer can go through this and optimize it. Okay, so it gives me true. It means we have all the weights like here are equal to the weights that are trainable. Now here, let's just quickly go through this example. Okay, here what I am going to do, I am basically going to pass these two sentences, and then return type is PyTorch tensor. Padding is equal to true. Padding will be applied to make the input value equal to the maximum input values. So that is why we have this true, and truncation is equal to true means we are going to cut the extra tokens more than the allowed limit, that is 512. Okay, or whatever you choose. Okay, so here is the torch.noGrade. I'm basically calling this torch.noGrade because we are calling this model not in the training, rather in the inference mode. Okay, so what I am doing now in this specific code, I am basically passing the input IDs from this pre-trained encoder plus the classification head. Okay, this classification head will now give us some random values because these are not trained yet, so we can't expect good values from this model. Okay, so what we are doing here, we are passing this input IDs, and once I execute this, it means I am passing the input IDs. Okay, it will be the batch size and the each batch size and its dimension. Okay, so we will have 2 and whatever the dimension, that is 768 in this case. Okay, so we will pass the batch to the model and the tension mask. Tension mask is basically used, let's say we have 128 the maximum length. Okay, and we get a text that is I like this. So I like this. We will basically the tokenizer is going to tokenize this text into three tokens. Okay, then tokenizer will auto embed two special tokens. One is CLS and one is SEP. Okay, and then wrap them in between these. Okay, so we are going to have now 5 token instead of 3. So basically these 5 tokens are, if we want to make them equal to 128, we will be adding around 128 minus 5, that is equal to 123 pad tokens. Okay, so we will add 123 padding tokens to this sequence to make it 128. Okay, and what this attention mask basically carries, it is the binary values list, you can say, where it will have, for this use case, it will have 1 2 3 4 5 and then all zeros till 128. Okay, so it says these 5 are the real tokens and these are the padded tokens. So later on in the attention scores calculation, just before the softmax implementation, we apply this attention mask. Queries will not be attending to those keys of the padded tokens. Okay, so it is a kind of restriction that we perform with the help of this mask attention in the transformers block, where we restrict the queries not to attend to the keys of the padded tokens. Okay, then whatever we get as an output, we are getting its logits and its shape. Then okay, let me execute this code and show you. Okay, so this is, you can see 2 3, we have 2 sentences. Okay, so 2 and 3 logits. So for each sentence we have 3 logits against the CLS token of each of this. Okay, so these 3 logits basically are, for the first sentence, for each class we get these okay, logits, and these are the raw logits again for the sentence 2. We can perform we can convert them into probabilities by applying the softmax. We will be doing all this, just stay tuned. Okay, then this tokenization function we are using to convert our data set into a tokenized data set. Okay, so we cannot pass the raw text to the model. Okay, so that is where we are applying this tokenizer function, where we will be passing tokenizer function these examples, like example.text. Whatever we get in the examples, we will be extracting the text part of it, and we will be applying the truncation is equal to true and padding to the maximum length, and maximum length, let's say in this case I'm applying 128 instead of 512. So I will be getting against each example in the let's say training data set, I will be getting the tokenized IDs, input IDs against each text. Okay, so let's say to this function, if this is my training data set, this is my trained data set. Here in this trained data set, let's say I have text column. This text column is basically the raw text. Okay, a string, but I cannot pass this raw string to the model to predict or to perform calculations on it. So what I need to do, I need to convert them into input IDs. Okay, input IDs. So here, this is what I am doing in this case. And when on the data set, this data set is basically, we calculated this, we got this data set over here. Yeah, see, this is, so if we call this if we call this function on the data set, this tokenized function internally, each time we are getting the train test and validation data in the examples and passing it to the tokenizer function, so it will give us the tokenized data. And what this tokenized data will look like, it is going to add some more values to it, the attention mask kind of data, input IDs. And if I show you, okay, so here, first of all, let's execute this. The function, it is going to see, it is basically applying this function on all the data. Okay, so see the train, test, and validation data. Okay, now if I show you this, you can see the data set previously had did not have the input IDs and the attention mask, but now we have these. Okay, now this input IDs basically is the input IDs of each example, not the raw text. Okay, so against each raw text example, we have now input IDs. Okay, and the attention mask of that data. Okay, as I explained. Okay, so now let's see what to kind of like keys we have in the each so train data set. We can see over there as well, but see these are the keys. Why I'm showing this, because the trainer basically object is going to ask for a specific column, that is labels, not label. Okay, so we rename the label to labels. Okay, then we do not need the text and the token type IDs. Okay, why we are not passing these to the model? So at the time of converting this data to batches, it will give us the error or irregularities. So we want to avoid those irregularities or any anomaly or any issue later on. So we just drop them, these two columns, and we, as we know, we are going to work with the tensors. So we are going to set the format to torch and then show you the data set. Okay, so tokenized data set, now I have converted it to labels, inputs, and attention masks. So each split has now these three columns. Okay, here I am downloading this data collector with padding it at the time of you can say batches formation. Dynamically it adds. So let's say if you in one batch you have 5 sentences, so the data collector will pad all the smaller sequences to match it to the maximum one. So what we do not basically use it in this specific example, because we are already setting the maximum length, so it will eventually make it to the 128. Okay, so okay, and this, I was getting some error internally. It was calling some torch vision, it was reading some kind of image tensors or something, and we are I was getting some library mismatch version issue, so I just make it false so I do not get this issue. So if you get the same issue, you can do this step. Okay, library mismatch issue. Okay, this is the step that is basically done by the trainer API internally. The time of execution of each batch, it will perform this step. It will extract the number of test examples, and here I am just I'm just looping over 4 examples from the train, and basically I'm just passing it to the data collector to make them proper batches. Okay, stack them on one another. So if I show you this, that is how it. So now you can see I have 4 examples, and 120 is the is the maximum length of this each sequence. Okay, so here you can consider it like I am now having four sentences, and each sentence is basically of 128 values. So it will be uh, 128 values. Okay, and we will have in the each batch we will have four of these sentences. Okay, so four of the sentences 128 values. Okay, so the maximum length. Okay, and the attention mask again to cover all the actual padding and the actual values or the real tokens and the padded values, so it must match the shape of the input IDs. Okay, then this is the labels shape, so we have four labels. Okay, each example gives us just one label that we can compare it later on um, with the prediction value. Okay, so internally trainer will does this step before before the execution of each batch. Let's move on. Okay, so now we have reached the compute matrix function. This compute matrix function is basically I'm using the evaluate that I previously installed, and from evaluate I am loading the accuracy and F1 score. These are some matrices that we use to calculate the accuracy or the performance of the model. Okay, so here what I am doing, I am basically passing the logits here. Okay, each time at the time of computing the matrix values, I will be passing the logits and labels. Okay, now logits and labels are basically um, these are the logits from the model, the output of the model, the prediction, plus the original labels. Okay, each logits is basically the number of examples just as we executed above. Uh, Against each sentence we will be getting three values. Okay, so labels will be just one label against each. Okay, so here I am unpacking these values like evaluate, and in this step specifically I am extracting the logits plus labels, because I need to extract the argmax, like the maximum index value of the logits, so um, I can compare it with the original labels. Okay, and I'm doing it on the last dimension. Okay, then I am calculating the accuracy score. So by simply calling this accuracy matrix dot compute predictions and references, I am passing these two, so it will calculate the predicted and the referenced label, and it will give me the accuracy score. Okay, with these two now I calculate the accuracy of and my F1 score of my model, and I return it. Okay, so each time I call it I will get the accuracy score and F1 score. So let's just execute this. Now here comes the training arguments. Okay, so this training argument is basically the configuration of the training parameters. You can say, you can compare it to a file. You have this file where you are adding the configurations of the training, and then you pass these configurations to the trainer. So these configurations will be used internally by the trainer to train the model. Okay, so output directory where we want to store the model. After it is done, what should be the evaluation strategy? So per epoch, one evaluation will be done. Okay, then save strategy, again one epoch. Learning rate, this is the learning rate. If you are familiar with the learning rate, this is what we use in the optimizer to optimize our weights. Okay, how many batches actually we want for training and evaluation purpose on our GPU. Okay, number of training epochs, here I will be just making it 0.5 to quickly train the model. To show you, I can make it even 0.2. So, and the task for you is to make it 3 or 5 and then run it. Okay, and look into the output. Then we have this weight decay or regularization technique. So then we have load best model at the end. Yes, we want to load the best model. What should be the criteria of loading best model. We want to have the model on the basis of best F1 score. Okay, logging step, we want to log values, just like we have for now. We will be having loss. Okay, we want to log these values for debugging purpose maybe. So 50 is the step. So after 50th step, actually it will be logging the values. Okay, and we can then later on check them as well. I will show you. Okay, and report to basically not reporting to any TensorBoard, or you can say ML flow. So this is just keep it none for the quick experimentation. This is the configuration for trainer. I am executing this like for the trainer now. Everything we have done so far. First is model. This model is basically the model that we downloaded, and we have with the encoder part with a classification head. Then we have this trainer arguments. Again, see, these are the training arguments that we just fixed over there with the help of training arguments class, and we are passing it to the trainer. Okay, so that is how you can pass it. Train dataset and evaluation dataset. So internally, trainer will be responsible for performing all these on the basis of all these configuration values. Okay, and then evaluation data set. After that, we are passing the data collector. Data collector, as I mentioned, is for dynamic batches. Internally, the trainer library will trainer object will be using it. Okay, compute matrix. I'm passing the compute matrix function. Okay, that I created over here. Okay, now I am going to execute the code. Now this trainer is basically ready to start training with. Okay, so we just need to call the trainer.train method, and we will be able to start the training of the model. Okay, so quickly checking the parameters device. So you can see the next, just like above, I am just getting the first tensor, trainable tensor, maybe from the embedding layer. Yeah, so I'm just checking if it is on the device, just quickly testing if it is on the CUDA. Yeah, so otherwise it will take a lot of time to complete the fine tuning. So next is, okay, this I was doing for just testing purpose. You can do it. Basically, this memory allocate gives you the utilized space on the GPU in bytes, so which is equal to 10 raised to the power 9. So I'm just basically converting into GBs. Okay, and if I show you, this is the data allocation for the model, and just by calling this trainer.train, we will get the train results. Okay, waiting for this trainer.train to complete the training, and here you can see your training loss and validation loss will be shown here, so you can monitor the training. Okay, once this training is done, what is happening during this training basically, so this encoder and this classification head, let me draw this here. Okay, so we have the we downloaded the encoder of the DistilBERT. Okay, and we also passed the number of labels and all the, so on the basis of those number of labels, basically the auto model for sequence classification basically is intelligent enough to find the classification head projections. Okay, so this classification head was also attached, but with the random values. Okay, so now when this training is being done, basically the data is passed through the encoder, then through the head, and finally the logits are being compared. Okay, internally some by default optimizers like Adam W and the cross entropy, I guess the sparse one, and these default loss and optimizers are used by the trainer and calculate the loss and again optimize the values. Okay, so by the end of this training we will have trained weights for this classification head. So previously when we were getting the uh, raw values of logits, now we will be having more accurate values. Okay, so okay, to show you here, you can see this is the accuracy and the validation loss here and F1 score here. So training, or you can say fine tuning of this model is done. So now quickly just showing you the history of the log. So you can see here we have this history of logs where we are basically, let me show you if the first one. So for the first one, you can see here at 50th step we are basically storing these logs. Okay, and that is what we pass to the configuration of training arguments. Okay, now with the help of trainer state dot best model checkpoint, you can find the best model that has been stored. So if you have more training epochs, then you can that this will be more useful. So here, if you see, this is the location, the local location that I have passed to the trainer argument, where basically I'm storing my model checkpoints. Okay, and this is the best. This is the F1 score against this best model. Okay, if you want to see the checkpoint at this, so you can see this is the checkpoint basically we stored. Now here is the quick example. So what we can do, we can simply call this pipeline from transformers. If you want to just perform this experimentation, let's say you can use this pipeline, and this pipeline has everything implemented inside. Okay, so if you quickly just want to load the model and test it, you can use this pipeline. Okay, you just pass it the model category, like here text classification. Then you, in this case, we have saved our model, so we will be passing the model directory and tokenizer already we have. So this pipeline library basically is the abstraction, okay, of all. So then device is equal to 0 again, though, so we want to pass it the CUDA. Okay, and if you want to pass the CPU, you can pass -1, so it will select the CPU. Okay, but we have the GPU, so we want to use it. Okay, so and then we have these three example sentences. Okay, I absolutely love this new font, it's amazing. And the second one is, this is the worst service I've ever experienced. And the third one is, this meeting is scheduled for 3 p.m. So I have one example for each of class. Okay, first one is positive, second one is negative, and third one is neutral. So let's quickly just pass these examples to the classifier that we just made from our trained model. Okay, see, we are passing the trained model, and of course you can pass the tokenizer because we are using the same tokenizer. So just passing it the classifier and then looping over this by combining it with the help of zip, and then I am showing you the text and its result from the model. So what model will do, model will be giving back a dictionary. I am just printing that. Okay, let me execute this and show you. Okay, so this is what I get after fine-tuning the classification head on top of the pre-trained encoder of the DistilBERT model. So you can see here, this is absolutely I absolutely love this new font, it's amazing. Okay, so it is positive, see, 92% of confidence, and it says this is negative. This is the worst experience. Yeah, correct one. And this is, the meeting is scheduled for 3 p.m. tomorrow. This is again neutral. So we can see we have trained our classification head with this sentiment based data, tweets data set, and now it's performing quite well on this, even on this 0.3 epoch value. You can perform 5 to 10 epochs, then it will perform better. Okay, no guarantee, but of course there are different techniques to monitor that, but I think you should execute at least 5 epochs and test this confidence score. You might get the more confidence value. Okay, so that is why we are having the loss value larger loss value, because maybe I think it's using the sparse cross entropy, and that is the negative log, so it punishes uh, the confidence. If the confidence is low, then it punishes it. Okay, so it is something like this. Okay, so this was it for for this video. I hope you have now idea of how we can use DistilBERT model and how we can fine tune it. So the same steps we are going to perform in the upcoming videos, where we will be using the same tokenizer. We will not be creating a tokenizer. We will just use the same tokenizer, and from that same tokenizer, we will tokenize the text, but the model architecture that we will be building from scratch using the PyTorch library. Okay, so stay tuned, and I see you in the next lecture. Till then, bye bye.